for which the combination becomes stationary, right? So that's a cointegration vector. And the reason cointegration is important is in a non-stationary world, cointegration helps us to identify, to define what economic equilibrium means. Okay? So if economic variables individually are non-stationary, that means shocks to individual variables have a permanent effect. Then the only way these variables could be related to each other is if they are co-integrated with each other. And if they are co-integrated, that means that there is an error correction mechanism which maintains equilibrium between these variables. Okay? So if there is any deviation from these variables, there is some mechanism which drives this deviation away. Okay? And that mechanism we call the error correction mechanism. So we saw some examples. So we saw this error correction theorem by Engel and Granger. Okay, so now, today we want to talk about estimation and inference. Okay, so I'm going to skip some sections which are not relevant for us. For 3.2, please cross this out. I'm not going to cover this. 3.2, 3.3, cross it out. And 3.4 as well. So we're going to start today with 3.5. Okay, so we said that, well, if there is co-integration, there is an error correction mechanism, and that underpins the equilibrium. And we're going to see how we can test for co-integration. But before we do that, it's also important to understand what happens if there is no co-integration. Okay? So we have, let us say we have two non-stationary variables, they are I1. And co-integration, we mentioned, well, that is a special case where the stochastic trends in x and y cancel out. Well, what happens if this special case does not obtain? It's a special case, so we don't expect it to happen a lot of the time. So then what can we conclude? What is going to be our inference if we do a regression? Okay, so what are the properties of regression models with I1 variables that do not co-integrate? Okay, it's very important to understand that. So suppose x1 and x2 are two unrelated I1 variables. Okay, they are I1, so they both have stochastic trends, but they are not related to each other, so they are not co-integrated. Okay, so if we do a regression of x1 on x2, what do we get for beta 2? The coefficient of x2, what should you get? 0, okay, if they are not related. Okay, but because they are I1, it turns out you do not get 0. Okay, so that's something very interesting. So ideally, if you do a regression of x1 on x2, we would like this regression to tell us that beta 2 is 0 because these variables are unrelated. But this does not happen. Okay, this does not happen. So this turns out not to be the case because beta 2 hat is not consistent. Moreover, as your sample size becomes larger, the t ratio for the hypothesis beta 2 equals 0 will indicate a significant relation between x1 and x2. Okay? So even though x1 and x2, they are unrelated, if we just do a simple OLS regression of x1 on x2, with a very high probability, you will find a significant beta 2. And if we are not careful, then we may conclude that x1 and x2 are indeed significantly related to each other. But such a conclusion would be completely wrong. Okay? Such a conclusion would be completely wrong. And the problem is that when the variables do not cointegrate, when x1 and x2, they are not cointegrated, this residual term is also I1. It is not stationary. Okay? And that creates problems so that you do not get a beta 2 equal to 0. So this problem is known as the spurious regression problem. Spurious regression. Okay? So spurious means false, misleading. Okay? It's not a real relationship. It is just a false relationship, but it looks as if it is a real relationship. So, as an example, consider two presumably unrelated I1 variables. Okay, so here is data for this 20-year period for the log of real private consumption in Denmark and the log of the number of breeding cormorants. Cormorant is a kind of bird. Okay, so the number of birds and consumption. Do we expect any relationship between these two? Economic theory tells us they should not be related to each other. Okay, but you do a regression of consumption on the number of birds, and what do you find? Test the null hypothesis, beta 2 equals 0. Well, the t ratio is 6.3. And if you compare that with a standard normal distribution, critical value, then you will reject the null hypothesis that this beta 2 is 0. And so that tells us that there is a positive and significant relationship between the number of birds and consumption. So you can increase consumption by increasing the number of birds in Denmark. Okay, so that seems to be a completely crazy result. Okay. Furthermore, if you look at R square, 0.69, so very high fit, right? Goodness of fit is very high. 70% of the variation in consumption can be explained by the number of birds. Okay? So these results are totally spurious, and they are simply a consequence of these variables being I1. Okay? If these variables were I0, it was a stationary regression, you would not get beta 2 to be significant. Okay? So this is the spurious regression problem. To understand this a little bit better, we can look at a Monte Carlo simulation. So first, let's look at the standard result, a stationary regression. Okay? So suppose we generate data series as IID variables. So x1 is epsilon 1, x2 is epsilon 2. Get a sample of size t. And these epsilon 1 and epsilon 2, they are independent drawings from a standard normal. So they are independent of each other. So x1 and x2 should have no relationship with each other. Okay? So you can look at different sample lengths here. Okay, so you draw these distributions and then you do a regression of x1 on x2. Okay, so you do a simple regression of this type and then you tabulate the distribution of beta 2. So in this IID case, you can see that right, the distributions are centered at 0, which is the true value of beta 2 is 0. And as the sample size increases, the variance of beta 2 hat becomes smaller and smaller. So that's consistency, right? So OLS is consistent as the sample size increases, the distribution of the estimator, its variance is becoming smaller and smaller. So asymptotically, it is converging to its true value of 0. And if you look at the distribution of the t ratio, then the t ratio converges to the standard normal as the sample size increases. Okay? So the standard asymptotic theory works in the stationary case. Okay? Now what happens in the non-stationary case? Okay, so in the stationary case, we see the distribution of beta 2 hat is centered around the true value of 0, and the variance becomes smaller as the sample size increases. And the t distribution converges to standard normal asymptotically. Now, let us look at the spurious regression. So x1 and x2 are independent of each other. So we have two independent random walks. So x1 is generated from epsilon 1, x2 is generated from epsilon 2. So their stochastic trends are different from each other, right? Epsilon 1 and epsilon 2. And we do a regression of x1 on x2. Okay? Then what do we get? Okay, so you can see the distribution is centered around 0, but as you increase the sample size, the variance is not getting smaller. Okay, so it is not consistent. It is not, the variance is not becoming small, so beta 2 hat is not converging to its true value of 0. Second, when you look at the distribution of the t ratios, okay, as you increase the sample size, okay, you can see that the t distribution is becoming, the tails are becoming longer and fatter. Okay, so you can see this red one compared to the black one has much longer tails and thicker tails as well. So what that means is, if you look at a value from this t equal to 500 distribution, compare that with the standard normal case, it's very likely that you draw something which is significant, okay, compared to the critical value because of these thick tails. Okay, so in this case, the distribution is centered around the true value, so it is unbiased, but it does not collapse as t goes to infinity. So it's not consistent. And the distribution of the t ratio is becoming increasingly dispersed, far from standard normal. So asymptotically, if you use the conventional critical value, you would almost always reject the null hypothesis that beta 2 is 0. Okay? And you would falsely conclude that there is a relationship between x1 and x2, when in fact there is none. Okay? So this example tells us that in a non-stationary world, it is very important. It is very important to what do we learn from this? To make it stationary, or if you can't, they are non-stationary, you have to test for whether they are co-integrated. If you don't test for co-integration, without co-integration, you cannot have any meaningful relationship relationship between x1 and x2. Either they co-integrate or there is a spurious relationship between them. There is no other possibility. Okay? If they are not co-integrated, there can be no meaningful relationship between x1 and x2 if they are I1. So it underscores the importance of testing for co-integration. Okay? Because without co-integration, you could have totally meaningless results. Okay, then I'm going to skip this 3.5.1. And let's go to testing for no co-integration. Okay, so without co-integration, we have spurious results. So how do we test for co-integration? So it is important to be able to test whether a set of p-variables, x1 through xp, are co-integrated. And if they are co-integrated, then you can move on to conduct estimation and inference. What is the co-integrating vector? Are they significant? Are the coefficients close to what is implied by economic theory? All those things can be tested, but the first thing is to see whether they are co-integrated. If they are not co-integrated, you can throw out your economic model right away. Okay, it makes no sense. So if variables do not co-integrate, then you can reject your regression model as useless and throw it out or modify it to get co-integration. So how can we test that? So we will look at some ways of doing that now. And the most common way of doing it is called a residual-based test. Okay. What do we mean by this? So definition of co-integration, so you have a vector beta, and if you make this linear combination zt, which is beta prime xt, then this zt, this linear combination, should be stationary. So what that tells us is, well, if this zt has a unit root, then x1, x2, xp are not going to be co-integrated. Okay? So if you want to test the null hypothesis of no co-integration, this is a typo, it should be no co-integration, not no integration. No co-integration. Null hypothesis of no co-integration can be translated into the hypothesis of a unit root in zt. Okay? And we already know how to test for a unit root using the augmented Dickey-Fuller test, which we have learned before. Okay? So that's the idea we want to use. Okay. And then, of course, you could also allow for a constant. Here, you could also allow for a linear time trend, depending on what x1, x2 look like. Okay, so generally speaking, you want to have a non-zero mean, so you allow for a constant, and so you get this zt, and then check whether zt has a unit root using the augmented Dickey-Fuller regression. Okay, so that's the standard thing, and then we know how to do the augmented Dickey-Fuller test. This is the ADF t-test with a constant in the regression. So you can compare this with the critical values, and we can do that. Now, if the relevant alternative to a unit root is trend stationarity, then you can include a time trend over here, and that will give you the test for no co-integration the ADF test with a linear time trend. Okay, same as before. Now what is the critical assumption? How do you get ZT in practice? To get ZT, you have to know what the coefficients beta are. Okay? Now, in some cases, economic theory tells us what the coefficients should be. Okay? There is some equilibrium relationship between exchange rates and price levels. Sometimes the theory will tell you, oh, the coefficient should be 1 or -1, and so on. Okay? Then you can form this ZT. Okay? And then you can do a unit root test, and then you know whether these x variables are co-integrated or not. Okay? So here, it is assumed that the betas are known to you so that you can construct this linear combination. So let's look at an example. Okay, so last time we saw prices on the orange market. So right, so we saw blue is the price of regular oranges, the red is the price of organic, and they seem to be moving together. Both are non-stationary, but they seem to share a common trend. And this is the difference between the prices, okay? And this looks highly stationary. So here, we are kind of guessing that the co-integration vector is 1 minus 1, because you look at the difference, and the difference seems to be stationary, okay? So we can apply to this difference, we can apply a unit root test, and we know if we can reject a unit root here, we know that these two must be co-integrated. Okay, so let's do that. So here's an example of a unit root test where the potential co-integration vector is known. Okay? So it's known, and the stationary variable is the difference between the prices. So intuitively, we think this co-integration vector may work. Okay? So 1 minus 1, and so we impose this vector, and then we obtain the value of ZT, and we test for a unit root in ZT. So now, in this, you don't want to allow for a time trend, because when you look at ZT, it looks stationary without a trend. So you just have a constant term. And then in the ADF, you have to take into account, you have to include sufficient lags, right, to correct for the serial correlation. So they do that, and then that's what they get as the coefficient on ZT minus 1. So they construct the T ratio based on that, minus 14.43. And this critical value, we compare with the Dickey-Fuller critical value. So here, something important. When we are testing for co-integration, okay, which critical value we use depends on the number of estimated parameters. Okay? So in this particular example, what parameters did we estimate? Well, the co-integration vector beta was known to us. We didn't have to estimate it. Okay? So here, the number of estimated parameters is 0. Whenever the co-integration vector is known, number of estimated parameters is 0, so we're going to use this row for the critical values. But if the beta is unknown, the co-integration vector is unknown, it has to be estimated first. Okay? And if we estimate it, then depending on how many I1 variables were included in the regression, we will look at the critical value accordingly. Okay? So here it is 0, so the 5, and we have a constant, so the 5% critical value would be minus 2.86. And we would compare that to the taking for the key ratio, tau c hat, which is minus 14.43. This is smaller than the critical value, so we can reject the null of unit root, which is the same as the null of no co-integration. Okay? So in this case, we conclude that organic oranges and regular oranges, their prices are co-integrated with each other. And the co-integration vector is 1 minus 1. Is this clear? Is it clear? Okay. Okay. Now, so this was a simple example. And what happens in practice? In most cases, the co-integration vector beta is unknown. So the above approach is not feasible. You cannot construct the linear combination Z, okay, if you don't know what beta is. So we have to modify the procedure to the case where beta is estimated, and that gives us the Engel-Granger procedure. Okay, so in the first step, what they do is they estimate the beta. Okay, now we know that OLS is super consistent. If there is co-integration, then OLS is super consistent. So in the first step, what we do is we estimate the betas by doing OLS. Once we have the betas, we can construct the residual, UT hat. And then we are going to test in the second step whether this residual UT hat has a unit root. Okay? So you test, we can test for no co-integration by testing whether the estimated residual has a unit root. And that's what we do with the ADF regression. Okay? Now, what is the difference between this and the previous case? Well, the difference is that because beta hat is estimated, that changes the critical values of the ADF test. Okay? So that is something you have to be aware of. And what is the intuition behind it? Why does the fact that we are estimating beta change the critical values that we have to use? So if we are estimating the beta, then the critical values change. What is the intuition? Well, suppose they don't change, then what could we do? Well, if you add more and more variables to the model, right, the model will become more and more, the residuals will become more and more small, stationary, going towards stationarity. So if you can include enough independent variables, you will artificially create co-integration. So to penalize the addition of extra variables, the critical values have to be adjusted, okay, so that you don't overdo it. So that's the idea, okay. So the critical values will change as we add more variables, okay. So as as more explanatory variables are included in the regression, the more parameters we estimate, the smaller will be the variance of the residual, and it will look more stationary. So in the test procedure, we have to account for that. So the critical values depend on the number of I1 regressors in equation 19. Very, very important. Okay, you should underline and highlight this. So that's why here we have the standard normal, and this is the dicupolar with a constant, the blue one. Okay, so that is the distribution we use when the cointegration vector is known. We don't have to estimate it. And then after that, if